Swayam Prabha. Digital India. Educated India.
Thank you, Sujatha, for a great talk this morning. I'm going to try and follow on from that, keeping with the idea of mobility devices and devices that enable people to move. Going back to that framework of disability interactions, the work that I'm going to talk about today really focuses on those 2 points of co-created solutions and then radically different interactions. And that means that it's quite early on in that design process. So the stuff that the talk that I'm going to give today looks a little bit at that discover phase, which is, I'll show you a little bit about what we did about when we started talking to people about products, and then thinking about how we came up with this problem statement to define like what we would do, and then a little bit of the development work. Now, we never got to the stage, or we haven't yet got to the stage where we're delivering any of these products, and actually, which is often the case, it's not a linear process. So as you begin to get to define, you go back to discover a bit more, and then as you begin to get to develop, you realize you have to redefine the problem statement. So we are moving between those places, but it's mostly in that space. So the talk is called "The Future of Tech is Squidgy." Everybody know what squidgy means? It means soft, like soft and squidgy. Like give you an example, yeah, like a stress ball or something, right? Like just soft. So we are squidgy. We are soft, right? Like you're soft, you're squidgy, yeah? I'm probably too squidgy these days, but I used to be less squidgy, I get more squidgy. So when we have any prolonged physical interaction with objects, we often make them soft and squidgy, right? So if you sit on a sofa or a bed and you get up, there's a little indentation, isn't there? You're often imparting this squidginess. And greater interaction with technology is the future. So we're going to have more and more interaction with technology. Things are going to become more interactive, right? So we're beginning to see clothing and fabric that's interactive. We're beginning to see shoes have sensors in them as you run, so it will track you. So we're beginning to see this embedded technology into more soft fabrics. And our built environment is also made to interact with us. So we're not like these, we don't want, as we go around, as we evolve, we don't really want to be Sylvester Stallone in like RoboCop, right? We don't really want to have these like massive, stiff exoskeletons. You saw some work before on exoskeletons. But if you had to put on an exoskeleton, do you want to be this person? Right? And you want to walk through the streets. You don't. You want it to just fit you, right? And move with you. You don't want it to restrict your movement. Now, So what about now? So in the meantime, at the moment we're looking at the development of prosthetics. We're not in that massive future where I can just click my fingers and a jetpack arrives on my back and I can fly off to wherever I want to go. So I'm going to look today at thinking about a little bit about prosthetics and orthotics, but actually the genesis of the work that we're doing at the moment on prosthetics and orthotics actually started with a grant on exoskeletons. So there was a grant called Wearable Assistive Materials, and the concept of it, and I was just a postdoc when we started that work. So it was one of those blue sky grants. There was a call for like blue sky ideas, and this idea was put forward between the Department of Chemistry, Department of Civil Engineering, Department of Mechanical Engineering, together at UCL. And so we're going to talk a little bit about that WAM work that we did, and then begin to think about what actually happened from that was we started to develop some thinking around soft prosthetic liners. And it's because some of the engineering that came out of that was quite fit for purpose. And so if you go back to that wheel, it also sort of speaks to that applied and basic research, because as we began to learn more about what users wanted, we could then update the problem statement and begin to develop more basic research in prosthetics. So rather than an exoskeleton, we started thinking actually, when we first started WAM, we thought about an exoskeleton that would help you walk, right? Like a lot of people do. A lot of people think that. But actually, the more we spoke to people, nobody wanted to walk. And actually, there was a lot of other use cases that were way more useful to people. So here's a video of Julia Barbareschi, a very good friend of mine, trying to use, I don't know if there's sound, but maybe. Listen to that. I'm going to turn it off because I like you all, but that is what it sounds like to use this particular exoskeleton. This exoskeleton had just been released onto the market in the UK. I'm not going to name the exoskeleton company. On the market, this was marketable. They were trying to get, listen to it, they were trying to get, right? They were trying to get, now, there's loads of things that are hilarious about this. One is the sound. So this is in the Gait lab. So I used to work in the Gait lab at the Royal National Orthopaedic Hospital. And I said to Matt, who's standing around the side there, who I would say, he was a very good friend, and he's one of those people, unfortunately, I've sort of lost contact with over years. But I'm sure if I picked up the phone, he'd become a good friend immediately. He's a lovely guy. And I said, I've got no money, but any chance we could just use the Gait lab one evening? Because I want to understand that this company is saying it's going to rehabilitate people to walk, and I just don't think it does, right? I mean, I think it allows movement, but it doesn't rehabilitate. To rehabilitate means to help me learn to move more, right? You know, when I really hurt my knee and I couldn't put any weight on it, I had to do certain exercises to build the strength up, and then I was able to use that. That was rehabilitation. You were making my knee work again. Does that make sense? If somebody had put something on my leg and it had moved it for me, I don't think that's rehabilitation. I just think that's a device that moves my leg, right? So we wanted to understand what that does. And we wrote a paper, which is funny, actually. The two papers, if you go to my Google Scholar account, the two papers that are most highly cited are the papers that we did on exoskeletons. And I can honestly tell you, they're not the most exciting papers I've ever written, but I think the word exoskeleton is exciting. So everybody seems to want to cite exoskeleton papers. So we put Julia in the suit, mainly because she was a PhD student. And also, she's a physiotherapist by background, so she was desperate to see what it was like. The other thing is, it took 45 minutes to put the suit on. Right? And this is when the company demoed it to us. It wasn't like us not knowing what we were doing. And the average physiotherapy appointment in the National Health Service in the UK is, guess how long? 45 minutes, right? So basically, all that would end up is that you'd have a heavy thing on your body, or you'd have to book 3 at least sessions, right? A session to put the device on, a session to use the device, and a session to take the device off. So you can imagine, I'm sure our healthcare system is, at capacity. We definitely don't have time to triple the time for an appointment. So, and also, it was claiming that it was going to make your muscles, stronger, better. So actually what we found, I haven't gone into it, but you can look at it because it's the second highly cited paper on my Google Scholar. It's very easy to find. But what we actually demonstrated was that whilst it allowed the gross range of movement to look a little bit like walking, the actual joint rotations and the muscle activation were completely different. So it wasn't going to allow you to build, it wasn't going to rehabilitate you, it was going to allow you to move. Does that make sense? So it shouldn't be used in clinical practice if your goal is getting somebody to be able to move into, their each limb independently. So, as well as having some fun in the Gait lab one Saturday and Sunday, we also thought, well, we should talk to some people, right, about what they'd actually want. So, this was a project that had a lot of different people involved, but this particular part of it was funded by the Engineering and Physical Sciences Research Council. Aspire Create is a centre in the Royal National Orthopaedic Hospital for spinal injury. So it has a sports facility that's completely wheelchair accessible, which these days isn't that novel. My local gym has a lift for wheelchair users and that's just a local council gym. It's not, I don't pay for a private gym. It's just the local gym has a lift for wheelchair users. We have lift access. We have wheelchair accessible toilets. We have changing places toilets. But 15 years ago, when Aspire was built, 25 years ago, it was quite new to have a ramp in the wheelchair, in the swimming pool, for example. And the great thing is, if you're in the spinal injury ward, you can just wheel from the ward into the sports facility. And then the sports facility can be used by anybody. We can go, wheelchair users can go. So it normalises just people in wheelchairs doing sport. Anyway, that's Aspire Create. And the Institute of Making is a great place which is run by Mark Miodovnik. But we started to think, well, yeah, what do people want to know? So we wanted to think, well, existing exoskeletons, what do people think about affordability, size, weight, speed, efficiency? And they basically said all of these things affect any functional application or usability. Like they're too expensive, they're too big, they're too clunky, they're too heavy, Like it's not an alternative to my wheelchair. My wheelchair works really well for me. Like I see no reason for it. So we ended up doing 5 focus groups, 6 healthcare professionals and 23 individuals with spinal cord injury. We gave them an introduction to technologies with photos, and then had immediate thought exploration. So we'd show them photographs of different devices and just get them to talk freely about what they thought. We did some specific exploration, so access to information or perceived hypothetical impact of the technology on their lives, ranking of exoskeleton features of importance, ease of use and characteristics versus perceived functional gain, material preference, view of cost. So we had these sort of deep dives with different people, and some of them depended on, like sometimes you'd bring up a topic and somebody didn't really have much to say about that topic, you know, that they didn't, for example, materials, they didn't know, so we'd have some samples of different materials, ask people maybe what material do they make their sofa out of, for example, which, you know, because people will choose leather or plastic or, you know, or fabric. And then we just asked them at the end, what were the expectations if there was to be an exoskeleton, you know, an ideal exoskeleton, what would be their expectations? And then after that, we did a thematic analysis. So generally our results were, and this is again a paper, but you can, short version is, any of the exoskeletons we showed them, they thought they were bulky, cumbersome, and obtrusive. Appearance would determine whether they used it or not. Like nobody wants to look like Arnold Schwarzenegger in RoboCop. People want to just look like a person that's going along the road. What they wanted was lightweight, low profile, pliable, so being able to move it easily, durable, so it wouldn't run out, and discreet. Weight is relevant for portability and for what's called donning and doffing, so like putting it on and taking it off. They were concerned about relying on a third party to trigger any movement, like anything like a motor that could break down and then they were just stuck. They didn't like that. They were worried about having no hand-free control, like being able to use their hands, hacking the control system. They were worried about people hacking their suit. They were worried about also the exoskeleton skin interface. They were really worried about that. I mean, any wheelchair user or prosthetic user will tell you that like pressure sores is their nemesis. That will prevent them from doing anything. So they were very worried. All of a sudden, their whole skin interface would be in contact with this thing. And then the critical thing was it needs to be faster than the wheelchair. Like, what's the point if it's not faster than the wheelchair? They suggested loads of things, a load of great things. Voice control, mind control, mobile apps, breathable for temperature regulation, pressure and temperature sensors, and nobody cared. There was no agreement about the noise. Some people cared, some people didn't care. You know, there was no particular agreement. So we came up with this idea then from that of WHAM, where what if we had a soft, active, orthotic material that could be used for many applications? And you can see that we've changed from exoskeleton to orthotic. Because what's not in there as well is some clinical case studies. So one of the clinical case studies was people who've had a spinal injury between about T6 and T7. It means that you're able to move your arms in one direction, but not move your arms in the other direction, because one nerve attaches to T6 and one nerve attaches to T7. So a simple use case was, can you just make the other movement happen for me? Does that make sense? So, and that's a really simple, in terms of mechanism, it's your elbow joint is a 1 degree of freedom. So it's actually a relatively simple movement. But could we do it with a soft robotic interface, for example? We thought that we wanted it to be a programmable actuation, have some intelligent, adaptable management system. Think about, can we have highly tunable mechanical design parameters, because people would be very different. Their muscle strength would be different, their body size would be different, so therefore the limbs would be different. So can we program that into the material? And make sure all of that is comfortable and discreet. Now, as you can imagine, we only had sort of 3 years to do this project, and the user studies took the first year nearly. So it wasn't that we were going to ever get to a finished product. We were just meant to be able to show at the end, and we did almost like a 2 centimetre square bit of material that's able to do this, because it was one of those very R&D projects. So this is mostly the work of Ben Oldfrey. So this was, as part of that project, Ben, who's now faculty at GDI Hub, he made squidgy sensors. That was his part of the project's job. So if you think about engineering across scales, we've got the human scale right at the top there, and right the way down to the nanoscale, right? And the material, and we need something that's going to go right the way across those scales, right? Because we're going to have to use some form of nanotechnology to enable the actuation. That's going to have to embed into some form of material. That's going to then embed into sort of the centimetre stage of, say, a liner or some sort of interface. And then that's going to go on to a human, which will be at the meter sort of stage. So you're going across these scales of engineering. So after lots and lots and lots of brainstorming and thinking, this was the initial concept that we thought we would try to make. And different bits of teams, I said there was mechanical, chemical, civil engineers, different bits of teams worked on different bits. So the idea was, could we have, right in the center there, you've got this embedded actuation. So the material would have some way of embedded actuation. Then we would have a modular localized sensor actuator management system. On the top, you'd have some sort of environmental sensing, so pressure, proximity, temperature. You'd need some sort of gel encapsulating the middle parts. And at the bottom, you'd have, you can see it's like ridged. That, when you go on the skin, would allow for airflow. But also this would maybe have EMG, maybe have strain, maybe have other sensors within it. And the idea would be that the outer skin is like your hand. It's a proprioceptor. And then the inner parts are like your muscles working effectively. So we're trying to mimic what the human body does. And so that's what we're trying to do. We're trying to get proprioception, but from a material. So maybe, you know, eventually we'd get an elephant balancing on a ball. I'm not sure we ever would. And so the bit that I'm going to talk about now is stretch sensors. So this is the bit that Ben worked a lot on. This is basically his PhD, was can we get stretch sensors that would fit into this material that would be relatively low cost, that could be used. And these are just examples of the many, many, many types of sensors that Ben made over the course of his PhD. Right, so he looked at very different materials, rigid structures with soft things inside, fabrics, conductive fabrics, lots of gels with some nano ferromagnet things inside them, right, so they could move. And so he just spent a lot of time. So like in these research meetings, every month he'd come in with like 4 or 5 new like things, trying to find something that worked. So eventually he stumbled on polydimethylsiloxane. I'm not very good at long words. My dyslexia gets bad, but PDMS as a substrate. So that would be the thing that would hold the doping agents that we'd put in to create these strain sensors. What's good about PDMS is it cures within 20 minutes. So any of you that's done any sort of lab-based studies, if something's going to take 2 days to do, we've got to go through hundreds of iterations to get to the version that we need. So something that will cure within 20 minutes means we can test things, probably a whole sensor in a day. And if it doesn't quite work, we can move on. So it's very advantageous for experimental printing work. So you have this substrate and you can print into it because it still won't cure for 20 minutes. The other good thing is you put the substrate down, and if provided your print's finished in a few minutes, it will stay within that substrate. And as it cures, it will stay in the substrate. And so then we used a flexible silicon elastomer within there, and it's part A, part B, 10 to 1. You mix it, and you get something good. So this was the silicon that we used. Silicons are often used for sensor applications as housing, as they're an inert sort of substrate for the doping agents. They won't react. They don't disintegrate as you put things into them. But they're also nice, and they're little. You can get skin-like ones. I mean, we had a lot of fun back then. Like we made casts of our faces with silicon. You know, we made casts of because you can get, and then you can actually make, because they do that in film industry, right? They make these sort of things. So we had hundreds of types of silicon, and we were just making various different mixes, and then doping it with different agents. So for the sensor development, we devised, this is taken from the paper, really it was a lot of Ben's work, devised a sensor development approach using doped elastomers, which could be printed directly and have similar mechanical properties to the original liner. That was our idea. We were going off of the prosthetic liner at this stage. So we had a polymer, PDMS, has a nice a low Young's modulus. So that allows us to put the conductive fillet inside with the nanoparticles. We had some metal nanoparticles. We also had some carbon allotropes that we tried. The composite material will conduct electricity when the filler to matrix content ratio is above the percolation threshold. So although you've got these materials, they're separate, but at a certain point when there's enough of them, the electricity can jump. Does that make sense? And you're able to make a full connection. So yeah, and that also reduces the amount of possible tunneling pathways that you get. So here's some images, sort of trying to build up how it would work, and then I'll show you a video. So you put down your initial substrate, you're building this up. This is you initially pouring. Got your glass substrate. You just got what are they called? Not a Petri dish, but you know those slides that you have in chemistry. Right, so those slides, you've got one of those. That's the slide. Then you add your silicon substrate, and now this is the printer, and it's just printing. And you can see this is the printer working. So we've got that silicon down, and this printer is just printing this what will become a conductive material inside the silicon. And then we move on, and you can see that we get this. I think that video could work. Yeah. So you begin to get a stretch sensor like this, right? So we end up with these stretch sensors that work quite well. Yep. And there's your stretch sensor again. A little bit of noise. So you can see that once we figured out a material that worked, there was then a lot of work done on what geometry will work well for the amount of strain that we might want to cover. And at this stage, although this was a difficult presentation to put together actually, because a lot of this work is written up in a paper for prosthetics, but actually the work was done initially for the exoskeleton work, but the exoskeleton work never quite got published, and then we went on to use those sensors in prosthetics, so we published it under prosthetics. But at this stage, when we were doing this, we weren't actually developing the prosthetic application. You just still had that concept in mind, that like 3D diagram of a WAM concept. And Ben was just working really hard to say, well, my job is to produce that stretch sensor and that the proprioception. So it would know, like if you had something here, it would be able to measure that stretch. There's somebody else's job then to have some sort of thing that will actuate it back. Does that make sense? And that's what he was just working on. So you can see here, this would just give you, I don't want to go across here, but this would give you these sensors. You know, you saw the video. Oops, this is caught somehow. This will give you one-dimensional. And then this would give you two-dimensional, because you've managed to make a matrix of them. Does that make sense? So these ones can only measure strain in this direction, this plane, because they're in one direction. Does that make sense? Whereas these ones have two layers. So you can go this way and you can go that way. Okay? So that's all very well, but they're quite, we've printed stuff which has a concentrate of particles in, but you're not going to be absolutely sure where each particle's gone. Does that make sense? Just some bits of those lines are going to have slightly higher concentrations than other lines. So how accurate do you think that stretch sensor is going to be? Not very accurate. So we need to figure out how do we make it more accurate. So that was actually done with a relatively, because we still had this idea of low cost. Like how do we make the whole thing low cost? We don't want to end up with, we didn't have an exact figure, but the exoskeleton I showed you before, that's $200,000 or something. We were just like, that's just ridiculous. So we want to try and just in the back of our minds always look at low cost. So this idea was it's just an Arduino circuit with some manual strain, just pulled on either side, and just be a weight, like and effectively what we ended up doing, I'm not sure if these are videos, but that just connects to a computer. We put these little red dots on, and even these little red dots weren't, they weren't massively precise. Does that make sense? There was a ruler and we stuck them on, but wasn't like a pick and place machine type of accuracy. I'm not sure if they're videos, but you get highly non-linear hysteric sort of performance, right? Not, like every time you pull it and you stretch it, there's loads of hysteresis in there, for those of you that know those terms. So basically you're not getting a repeatable performance. That's effectively it. And not only is he not getting a repeatable performance, it's changing sort of erratically in a time period, and over time that erratic period is changing as well, right? So it's quite a complex thing to fix. And so what Ben worked on a lot was how would we maybe use a neural network to fix that? And in the end, he went with a long short-term memory recurrent neural network. And the reason for that is partly due to the fact that time shift I was talking about, it's very good at learning in the time domain, and so therefore it learned more quickly than other neural networks that maybe don't have that time domain knowledge. So in the end, we were able to get to the point where these red dots and blue dots are where we would predict. Does that make sense? Like where the model that we ended up with would predict where the dots would be. And I think that was probably his first paper that he published, which is a deep learning approach to nonlinearity in wearable stretch sensors. And that then was proven, but that paper only, he's still writing. It's one of those things at the end of your PhD, you never write up the final paper. It's just one of those papers that never finally gets there. But that was just one-dimensional, this paper. And there was a second paper coming which shows the 2 dimensions. The work's done, the paper's on the way. So yeah, so we did the calibration, and so at that point, and a lot of this work, as I just said, was written up in this paper. That's why I put it up there, because the WAM stuff sort of didn't quite, it was sort of nearly finished by the time, the WAM project ended halfway through Ben's PhD. So the sensor development continued, but he continued on working on a subset, which was then prosthetics. So in prosthetics, oh yeah, sorry, just 2 other slides quickly. There were some other things that we did, and you can have a look at this, which was bespoke force sensing. So that was Strench. We also did some force sensing, and there's actually a really good video if you go to the IEEE sensors of this paper, where we developed the sensor in like 2 hours, and anybody else then could use it, but again, with low-cost materials. And that was all, at the time of WAM, that was all going to be integrated into this sort of type of multimodal skin concept. That was the idea, that we would bring all these sensors together, and then they would go into this final WAM content. And just to give you a sneak peek of what was happening on the other side, which was trying to do the chainmail, because you're sensing, but then you've got to move. There were some people looking at the chainmail dimensions, and this again was published by them. And they began to look at how we could make, there's the citation. I have to say that I don't know this work very well, so I haven't put many slides in it, because they were working on just trying to get these 4D printed magnetically functional chainmail for the exoskeleton. So our idea was maybe we could just use magnets to do the movement. And that would work as well for people with stroke, because you could hold a magnet and you could then move your own arm. Does that make sense? So your other hand works. So you could use that to move this. And you'd be able to use the magnet to sort of, decide where your hand might go. So those were the kind of use cases that me and my team were feeding in. And then these guys were creating these materials. And this was this ferromagnet. Can't hear the sound, sorry. So you can see here that that's a magnet, and he's trying to show that as you bring it closer, it will sort of articulate. Does that make sense? But again, these were really, and you can see here, this is like 10 millimeters defection of a beam on the right-hand side. So you've got this fixed surface here. It's fairly rigid. It will flop down, and then a magnet will bring it back up. Does that make sense? So, or the other way around, depending which way you attach it to the end point. Yep, and these are maybe not videos. Oh, here's the video. And so this is Mark Ransley, I think is his name. He's a different PhD student, which I didn't work with him that much. But this is him showing that actually there's another way of doing it, which would be just to apply voltage. And then these linked chainmails are actually just 3D printed chainmails. There's nothing smart about them, but you connect them in a certain way, you apply voltage, and then that would work. And that was another concept design that we had for that chainmail. And all of that was going to go into the WAM concept. But what actually happened, which is what happens with a lot of research projects, as Sujata was saying earlier, you have postdocs or PhDs, they move on. We got as far as basically demonstrating all the component bits working, and then you would have needed an extra 5 to 10 years of funding to bring it to market. And we just didn't have that, we didn't get that. And the person who was leading this grant, I was still a postdoc when this was happening, they moved on to other things basically. And then the project just didn't go much further. But there was a bit with the sensors, and Mark Miodovnik and I and Ben went, hang on, those sensors could be used in other things, because at the time, this was literally just when I went from postdoc to lecturer, is at that time of my career. And I had just got this new PhD student called Reese, who was one of my first PhD students. And Reese had started looking at prosthetics. And yeah, the next couple of slides are all Reese Williams, and that's his thesis, if you want to look at it. So a lot of really good work in his thesis on thermal comfort. So I get an amputation. all of a sudden, I need to attach a limb to my leg, right? Now, I said at the beginning, we're all squidgy, right? So I don't want that cup, that rigid cup going on my skin, do I? You don't want to, when you buy shoes, they're not made of Lego, are they? They're not that rigid plastic. You buy soft, relatively comfortable shoes, right? So in order to have that cushioning, but at the same time, you need rigidity, right? Because you've got to stand on it, and we're quite heavy, so you need that rigidity. So you end up with a liner. So a soft material, like when you put socks on your shoes, so you have this soft material, and then that soft material cushions against this hard thing that's going to take the mechanical load. Now, when I used to think, before I'd ever seen a liner, I knew this conceptually. Like I read it in books, I'd read many physiotherapy books, occupational health books, and I knew that liners had to be liners. I've got one in my office. They're heavy, right? They're like, a good centimetre. Do you know a wetsuit? Has anyone put a wetsuit on? Has anyone put a wetsuit on? They're really hard to put on. They're like, you put like talcum powder on and you're kind of squishing your leg in. And then once it's in, it creates that nice seal and it's fine. But it's stiff and awful, right? It's really stiff and awful. Have you ever had a really thick bandage on a bit of your skin? Imagine that, only the material's making you sweaty, right? And it's heavy. Like when I hand it to you, you won't expect it, to be as heavy as it is. So it's not like a sock. It's like a 1.5 kilogram weight that you've got to attach to your leg that's going to suck around your stump. And the other thing to remember is amputations mostly aren't clean-cut things, right? So they've either come from maybe a cancer growth. So imagine you've got a tumour and then the surgeon's trying to cut around the tumour, trying to preserve as much of your bone as possible, but obviously you're going to get different sort of edges of your bone, and then your muscle is going to end differently. And so every limb is different. Like if you had a car accident and it had to be amputated, if you were born without a limb, still some of the bone has grown, right? Some of it's worked. And also you've got different levels of sensing. So that proprioception thing, some people have no nerve endings. So they have no idea that they're getting pressure sores. They don't feel the pain because there's nothing to tell their brain, hang on, that's really rubbing. And like I've seen people go down to like nearly the bone sometimes on different things where they just didn't know because they've got no sense of it, right? But the thing that Rees really cottoned on to was this idea. Sorry, this is about the liners. So the liners are they've got superior skin adhesion, so they don't move, which is good, right? Because you don't want something moving all the time, because that will obviously create a sore. They do distribute the load, so they are like a pillow. Like if you jump on something, it does distribute the load, which is better because of what I just said, where you're going to have different, like imagine a knuckle. You want to sort of distribute that load across, and it does form a seal, which is a good thing because then you're not getting bacteria or water, rain, anything in there. Ultimately, it allows reduced shear stress, and that's really important, and it gives higher cushioning effect on those bony prominences, which is what you want, right? So if you ever put your hands under your bum, right, you'll feel that there's two pointy bits called your ischial tuberosities, and you'll find that if people lose a lot of weight, that part can get really sore, like really elderly people, that part can get really sore, the skin can get really loose because you haven't got the cushioning. That bit of fat is actually really useful. It cushions you against a very pointy thing when you're sitting on it. So if all of a sudden you've got pointy bits in your leg that you weren't expecting, that can cause a lot of problems. So what Rees did was he, went out and went, hang on, there's 2.3 million people in the world who use a prosthetic. So let's talk to them. And he spoke to a lot of people. There's one woman he met who had diaries for every single prosthetist visit. For this day, I've wanted to go back and just analyse those diaries because she was in her 70s. She'd always used a prosthetic limb. Every single change had been noted. But when he started talking about thermal discomfort, he said basically it had a lot of problems. And actually, a previous paper had linked it to both depression and anxiety, but also not using people's limbs. Like they stop using them because of this thermal comfort problem. So you might think, well, thermal comfort, what's that? That's like how hot or cold the skin is. Okay, that's going to be a bit annoying. Like if you get a bit too hot, like, I don't know, when you're in a room or if you had to go out into the corridor and take a meeting like Sujatha did yesterday, at some point it's a bit uncomfortable. But uncomfortable is not a medical problem, is it? It's not a big problem. But what we were finding was that some people had excessive sweat, often due to the way that their skin infrastructure was in place, so they might get excessive sweat. So you'd hear stories of people having to take their leg off every half hour and empty the sweat, right? Which is not a nice thing to have to do. It also had a lot of wear and tear and different prosthetics displacement. So as you get hotter, do you ever get too hot and I don't know, like when I first got here the other day, went to the hotel room and I tried to take off my rings as I was getting into the shower and they wouldn't come off because I was too hot and, you know, it was hotter than I'm used to and I'd sort of swollen ever so slightly. I just got a little bit bigger. So you can imagine if that's getting bigger, then if you put it on in the morning, but then what happens when it gets cold is it retracts and it can fall off, right? So the limb can literally slip some moments, then you go outside and it sticks, and then, you know, it's really difficult. It also is causing skin damage. So you've got a hot, sweaty thing with a little bit of movement. Like, it's a joy for bacteria. Right? And also then for like causing any kind of cut or tear or pressure sensor. So reduced wearing experience. People just got miserable wearing it. And often led to just general overheating because the body would then overheat because one part of the body was overheating. So some use cases or some stories that we heard were people saying, do you know how embarrassing it is? Like you go on a first date and your leg smells? Like, or you're going in for a job interview, but just as you walk in, your leg slips and you realise that your leg's full of water and you're just sitting there knowing that's happening, you know? So it really isn't, like it's more than just a mechanical problem or biomechanical problem. So we had this idea of smart prosthetic liners. So as I said, Reese was just finishing his PhD and he'd been doing this, and there's a whole other presentation I could give you on work that we did for that, which was very much about developing sensors that we could then test heat profiles over weeks, and as well as qualitative work. But for today, I'll tell you that when he finished his PhD, we had this problem space of thermal comfort that we knew was a real problem, and we had these sensors that Ben was producing. So we thought, well, let's see if they would go together. And we actually applied for a little bit more money, which was with the StarWorks and the Aspire people. And we started thinking about developing this smart liner. So you can see that Ben's sensors are here. Can you see? Here and here. So they're measuring strain, yes, in one dimension, but in different parts. Does that make sense? And you might even have different types for the different, oops, sorry. Don't know how to go back. Yeah, you might even have different types for different areas, you know, so this was the idea. Now, what do you think this blue bit is? These blue lines. It wasn't a spring, it's a good guess, but it wasn't a spring. Left one? No. It's a cooling channel. We wondered if we could have a heat pump that would actually cool the material. So we knew that overheating and perspiration caused skin breakdown. We also knew that, because the grant that we applied for was specifically for children, so children are a great problem space for these stretch sensors, right? Because we need to know when their limbs need to be replaced. So we need to know how much they're growing. So it makes sense on multiple levels that the liner could actually measure human growth as well as the problems that we had. We knew it should be bespoke, and getting back to our squidginess, we're all soft, so we don't want to make something hard. So going back to that slide I showed earlier with elastomer liners, the bit that I want you to focus on now is that the distribution of interface stresses between the residual limb and the prosthetic socket of a transtrivial amputee has been considered a direct indicator of the socket quality, fit and comfort. So we were very focused on that bit. We know that if we can get that right, then we'd have a better quality fit, and that's not our work, that's somebody else's work. So this was the idea of the low-cost, bespoke, fitted liner. This would be the active cooling system. This would be the integrated growth tracking, and we would be able to calibrate all that based on Ben's previous paper on deep learning. That was the concept. That's what we came up with on a blackboard. So the next steps then were, well, we're going to have to make a mold, aren't we? Because we've got to make the liner. So we need a thing to make the liner in. We then are going to have to figure out a way of making these elastomeric fluidic channels, again using printing, because the Institute of Making and Ben love printing. And then we're going to have to think about how we incorporate these nanocomposite stretch sensors. Those were kind of the steps. So we went to a hospital where, with a clinician, Stanmore Hospital, we scanned the limb. a residual stump of a child, oh, actually of an adult, but we scanned the limb, adults to start with and then children, and then we cleaned up the file. So you need to clean it up to make it suitable. And that was done with the help of the prosthetist, because obviously we're engineers. We don't know how those loads should be distributed or what should happen, and that's what somebody trains for 4 to 5 years to do. So they did that bit. Then we had to extend it. So because we'd taken the scan, we were going to make a mold, then pour silicon into that mold. The silicon was going to have a thickness, so we needed to make the scan a bit bigger for our mold, so that when we put the silicon in, we'd end up with something that would fit this limb. So we extended it on the distal end by 10 millimeters and at each of the sides by 2 millimeters, because we thought the liner would be 2 millimeter thick, and that at the bottom you always want an extra bit of thickness for that load impact distribution. Okay, and then from that we made a mold. So we made a mold, got some plaster of Paris, made molds, and then inside the molds we poured silicon, we left it, and then we cracked it open, and then we had this blue silicon. Well, it looks blue in that picture, but that's because it's still sitting on the blue casing. But we had this silicon liner that we could begin to work with. So then the idea was, well, so we've got that bit, how do we then get this fluidic channel printing? What will that look like? So we began to print into these little channels. And you can see this is, at the beginning, it was just a 220 by 120 centimeter fluidic channel. And then we were able to integrate that into the mold. And then this should be a video. One of these should be a video. I think one of these is a video. This one. So this is the pump. So this is just, I mean, these aren't, obviously, if you was ever going to go to market, this would be a lot smaller. This is just demonstrating the principle. And the fluid that we're pumping around is blue, just so that we can see it. But this was I don't know if you've got sound for this. I'm not sure which one I put in. But yeah, you can see that this cooling fluid is moving quite nicely around our mold, around our liner, sorry. And then we did some thermal imaging on that to see how much we could reduce the temperature, and how long it took to reduce temperature, and how that dissipated, and things like that. And all of the details of that thermal imaging work is in the paper. You can have a look at it. And so then the final bit was putting all of this together. So we also had to integrate the stretch sensors. So the way we integrated the stretch sensors was when you have the mold, the next thing that we did was we stuck the sensors around the mold, and then we poured the silicon in, and then they were embedded in there. And so we were able to demonstrate that. And again, it's all in that paper that Ben wrote. And so effectively, now what we're doing is beginning to think about device level testing, what geometries or sensors or sensing are useful. So although we've got some stretch sensors, do we want to put other sensors in there? Or is there anything else that is needed? Printing embeddable sensors and cooling sheet as one. At the moment, we haven't demonstrated that. We've done them as two separate things. So it would be good to get a multi-head printer and be able to do both at the same time. And also, can we print directly without the need for a cast? How would we manage that? They're all things that we're beginning to think about. And that would then allow us to come up with this idea of this embedded skin idea. So one part of that is happening, so that's the whole team. So for example, Richard Jackson and Anna and those, Richard and Anna worked on that chainmail. Deborah was the occupational health therapist. Mark is the lead of all the material science bit. Zule and Debbie did the work on the user-centered work and what the use cases were. And then Mark, Imad, Mark worked on those, the chainmail, and Imad and Peter, Rui, they're all clinicians, clinical facing people. Rui's technically an engineer, but in the hospital. And Roz at Stanmore Orthopaedic Hospital just helped us with getting patients, allowing us to be in the hospital, talking to people. And also all the focus groups were with staff from there. So there's a video, which I'm hoping will play next. It will work. This is purely Ben speaking. I thought you should hear from Ben directly. He recently got awarded his first sort of small grant as an academic. And it's just talking about what he's going to do with that money.
Yes, so my name's Ben Artery. I'll be giving a quick overview of our project. algorithmic design of functionally graded prosthetic liners, which is a collaboration between groups at University College London, University of Southampton, and Radii Devices. So in prosthetics and orthotics, the use of digital manufacturing is rapidly accelerating, really exciting things happening. However, it's still focused on the rigid material prosthetic componentry that's available. And the thing is that we're soft. And yeah, we're interested in what we can do in terms of soft technology. Yeah, this slide, yeah. So the interface between the residual limb and the socket, or is often called the stub-socket interface, it still presents a lot of challenges around comfort, fit, and more and more people more ubiquitously are wearing soft elastomeric liners between the socket and the limb that help to reduce shear stress on the skin, increase comfort, and they just, for particular areas, they give a high cushioning effect on the bony prominences. But how could these be improved? Particularly maybe, thinking about people that have residual limbs with troublesome topologies, shapes that are difficult to fit for prosthetists. There might be heavy scar tissue, or the residual limb volume might be varying greatly. I mean, they do daily, they do seasonally, but what could be done? So next slide, please. So looking to nature, let's think about those tissues that are actually in the residual limb or other parts of the body, other parts of nature. Well, nature creates these incredible interfacing mediums between hard and soft materials in the body by grading between the connecting tissues for different reasons in different places. And thinking about our problem, well, this grading of tissue, what it does is it spreads the stresses being translated. So rather than concentrating stress at a specific point, it spreads it across that interface, which has potential to increase the possible force transfer at an interface and reduce the tolerance to damage, because it isn't creating these maxima of stress or the interface between different components within the device and onto the residual damage. Next slide, please. So additive manufacturing is now, it allows, for us to think about these things with multi-material printing, structurally complex products that we couldn't previously create. So we're really interested if we can incorporate these ideas into the technology for the stump-socket interface. We want to look at ways of, potentially making bespoke, optimized material properties across the interface that could be created for the varying tissues of the residual limb. So, this could be grading perpendicular to the interface, although thin, that's one area that we're really interested in exploring, potentially really creating very, very soft materials up against the residual limb, and otherwise, something a little bit more akin to the socket at the other side. But maybe that's not we want to explore whether that's the right question to be asking. Also, if there's parallel to the limb, if there's different tissue properties around the surface of the residual limb. But really exciting is to be able to think about programming the material properties of the liner interface, dictated by the local properties of the residual limb, the needs of the user, and their use type running, for example, to sense different problems within the socket as opposed to warping or otherwise. So next slide, please. And so really, along with these new ways of manufacturing, across the board for all components, really, we need newly applicable repair strategies. We need to devise these if we're not really going to be exacerbating what is also a really real problem in the repairability of these devices. For liners, repair barely happens at all, and that's okay maybe in some settings. But for the liners, these are replaced once, twice a year. It could be more frequent than that. And this adds up to a great amount of waste and expense over the lifetimes of users. And if we're thinking about more advanced technologies, we need to be reducing the value and the cost that we're putting into that. We need to be fixing these things rather than just throwing away something more expensive. And at the simpler end of simply allowing a product to be available to somebody in low resource settings, well, this low continued use of the device, it puts up huge barriers for potential users in low resource settings. And if we can be fixing something and creating efficiencies and costs, then that can open up liner technologies in these settings, and it also has a knock-on effect to other socket technologies, for example, that require a liner to work. Okay, next slide, thanks. So, therefore, building on the materials development work that we've done at UCL, on soft material structures, liner technology, and exciting predictive socket design and modelling work that's been done at University of Southampton and the now spin-out company Radar Devices, we aim to the following with this project. So we want to model and produce new functionally graded material interfaces for improved comfort of the socket interface, along with developing repair strategies to match these advanced manufacturing techniques. The objectives are to fabricate a set of novel graded patches, model the socket interface with respect to optimizing the stress profile, want to develop a device level custom testing line for implementing these developments, and finally look at a repair and maintenance technique appropriate to these material structures. And then the next slide, please. Yeah, and then that's our team there. So looking forward. So myself and Alex and Elsa and Joshua will report back when we've made some progress. Thanks very much.
So, well done, Ben. That was Ben's latest. Ben's latest. Come on, let's move on. Ben's latest